Okay. So, yesterday we saw two objects. Firstly, this concept of Gelfand transform, namely it starts with a commutative Banach algebra A and we denoted this by F, where one starts with an, so F of x is x hat. These are space of non-zero homomorphisms and x hat of omega is omega of x. Then we noted that norm x hat is less than equal to norm x, and for C-star algebras, after this was the motivation for introducing C-star algebras. So, it is a star algebra and so on, but most importantly this identity holds. And then if x is normal, then this is already the spectral radius. So I wanted to draw one useful corollary of this, and then of course we will move towards examples of C-star algebras. So corollary is that at this moment I am keeping this unital C-star algebra because I have not proved that for a C-star algebra I can unitize. So for a Banach algebra, of course, we considered A tilde, which is A direct sum C, that is a unital Banach algebra containing A. Similar thing holds for C-star algebras. I have not proved that. So we have this unital. Later on we will remove that after proving that unitization. So let A be a unital C-star algebra. Then the C-star norm on A is unique. That means that there cannot be two norms. So two norms, say norm 1 and norm 2, such that both turn A into a C-star algebra. And that is so because maybe even this part is enough. So what is this quantity? Suppose let us take an arbitrary x, say, then norm x square is like norm x star x, say 1, 1. Now norm x star x is self-adjoint, therefore it is like the spectral radius of x star x. Now this quantity does not depend upon the norm of the algebra, it is an algebraic quantity. One kind of spectrum does not depend upon the norm. So this is same as x star x2 and okay. So this norm is unique, and maybe another consequence of this is the following. Now I have two C-star algebras and phi is a star homomorphism and unital, then spectrum of phi A is contained in spectrum of A. That is easy because if lambda minus A is invertible, you fix an inverse here, then push it by phi, that gives an inverse there. So this is so, and this implies that norm phi A is less than equal to norm A. So star homomorphisms are automatically bounded. Okay. Now we start with discussing examples, and today we won't do any theorems or any propositions, we will just discuss examples of C-star algebras. So first example is called non-commutative torus, and this C-star algebra played a major role in the development of this subject called non-commutative geometry. Kind of it allowed people to form intuition about this subject. What kind of propositions one should expect, so one always tests this against this C-star algebra. So we will discuss this, but construction of this kind of involves a principle, and that principle is very useful, and it is used in fact in all the examples. So let us fix an irrational number theta. And now I define the C-star algebra. Of course, one has to prove its existence. So A theta is the universal C-star algebra generated by two unitaries U and V such that UV equal to e to the power 2 pi I theta VU. So what does this mean? This means two things. Firstly, A, so that this C-star algebra A theta contains two unitaries. They satisfy this condition, satisfying this condition. Okay. Secondly, the star algebra generated by U and V is dense in A theta. Thirdly, if A is another C-star algebra such that there exist U tilde and V tilde in A, there unitaries, they also satisfy the same relation. And star algebra generated by U tilde V tilde, this is the notation for that, is dense in A, then there exists unique surjective morphism phi from A theta to A such that phi u is U tilde, phi v is V tilde. So, this is the meaning of first two lines generated by UV, and third line stands for this universality. Now, of course, question is that how do we know such a thing exists? So, for that the principle is the following. One first produces a star algebra generated by U and V such that that relation holds. This is an algebraic construction. So, if you want to produce some algebra satisfying certain identities, what is the rule? Suppose you want to have some identities. So, identities are given by, suppose you have some letters coming from this set S, letters coming from this set S, and then you have a collection of words W. Then you want to form an algebra such that these relations are satisfied. So, what you do is you form the tensor algebra on this, you consider the vector space generated by with S as its basis, and then you consider the tensor algebra and the ideal generated by these words form the quotient. So, similar construction, and you form this algebra A finite. And now, yes.
I am sure there are large percentage of the audience who don't know what tensor algebras is or what the quotient is. So maybe
Okay.
explain those the concepts a little more, or in the specific context say what it means.
Yes. So, yeah, that is easier. You consider, in this case, of course, it becomes much easy. So, suppose you consider things like words in U star, V star. So, what is a word? What is like a finite sequence like U, then U star, V star, and things like that. So, they will form now these objects, and you can consider the complex vector space generated by words, and now of course you can multiply two words by concatenation, and then you can define a star structure, because if W is something, then you define W star to be the word N star and so on. So, this gives a star algebra, and yes.
Before that, would you like to give two concrete unitaries or leave it as homework or something?
I have not yet done. I have not yet done.
No, this.
That's what I am
you
doing.
give it to unitaries.
No, no.
Either give,
No, in the definition, in the definition you do not give. In the universal picture, you do not give any concrete unitaries. It is just defined like that, and it comes in the proof. So, you fix a separable Hilbert space H, and now you consider this set, which is where pi is a star representation. That means this is an algebra, so this is algebra homomorphism. Pi of x star is pi x star, and of course pi is linear. First claim is that pi is non-empty. So, for that you consider this Hilbert space H equal to L2 of R. Yeah. And now you define two unitaries, namely U of f at S equal to f of S plus 1 and V of f at S equal to e to the power 2 pi I theta S Fs. Then let us write down what is UVF at S. This is like U of VFS, so VF at S plus 1. This is and VU at S is like so these two operators satisfy this condition. And this proves that this set is non-empty, and now define a norm on Of course, one has to verify that this quantity is finite.
Arthur, 1 second. On that Fn, did you also impose the requirement that U star and V star are ideal?
Those are unitaries. These are unitaries. Yeah. Unitaries.
You don't actually have a C-star algebra.
And in a star algebra, I can define unitary.
So you just mean that condition U star equal to U star U equal to
V, yeah. So that norm is finite because if you consider, say, an element so you fix an element A that will look like, and this is a finite sum. Then norm pi A is less than equal to So this is finite. And now you completion of with respect to this norm. Of course, this will satisfy properties A and B. We will prove C later. Once we prove that every sister algebra sits concretely inside some Hilbert space, we can prove C, so we will prove C later. Here there are 2 points which one should be careful about, and that is a set theoretic point. One must fix one copy of a Hilbert space, and kind of it is fixed, and in meaning depending upon the situation, in this case it is enough to fix one separable Hilbert space, but we will see other examples where this will be replaced by some cardinal number, but this copy needs to be fixed, otherwise this is not a set, and therefore this is kind of meaningless.
So if the cardinal numbers are different, then
If the so cardinality will be dictated by cardinality of these relations.
and then norm will be different.
Which norm?
No, if the cardinal numbers are different,
In this case, of course, one can eventually prove that instead of separable, so let us fix some other cardinal number and some other Hilbert space H.
then the norm will be different.
In this case, one can prove that no, the norm will remain same.
Oh,
But one has to fix one. I cannot vary these spaces. That is fixed.
So you are not starting that U and V are sits in the different Hilbert space. You are just assuming
U and V are not sits in the different Hilbert space. You have to fix. So you have to fix. Now you have to fix, put L2 of R, but you have to fix it there. It is fixed. It is fixed, and
L2 of R, if you take the, these two operator U and V and take the sisters divided by these two,
yes,
and there is a norm.
yeah, there is a norm.
But he is trying to prove that universal property. He is trying to say that there is a sister algebra with that universal property.
No, right now what I am saying, no. Right now what I am saying is not that. It is a kind of. It is a representation. I just proved that in a separable Hilbert space, I can produce a representation. How do I do that? So this is a separable Hilbert space. I have produced a representation. So that shows that this set is non-empty.
So that's why I am asking that. You assume that U is acting on the L2 of R. Initially.
Even here?
Yeah.
Yes, that is my copy of separable Hilbert space. So I take all representations in L2 of R, but the Hilbert space must be fixed. And if you want kind of more elaboration on this point, one should look at some book on.
You said you have to fix the
You have to fix the Hilbert space. Now Hilbert space is L2 of R.
What you are saying is you were saying that Hilbert space has L2 of R.
Otherwise, you can fix anything, but then
And then transport the
exactly by some unitary you can transfer.
That's why I am saying.
But the point here is that it is a fixed Hilbert space. Okay, that is the point, and kind of one should invest some time in understanding this remark, because otherwise, why should I make this and kind of. So it makes very good sense to understand at least what are basic axioms of set theory, and this is called, because of restricted extensionality, this is a set. Otherwise it is not a set, it is like kind of Russell's paradox kind of thing. So one should be careful there. And yeah. So second example is also in the same spirit. In the first one, I did not attribute any name because it is really, I do not know who are the people responsible, but it started with Paschke, Riffel, and so on.
Wimsner, Voiculescu.
Huh?
Wimsner and Voiculescu, not
Yeah.
operator.
What?
Yeah, so we made this A finite to be summation.
which satisfies C star condition. Now I can complete that, and that gives a C star algebra, that is A theta. So universality property I have not proved, that's what I just wrote down and which I have erased. So we will prove this universality later on. So we know something about C star algebras. Right now we do not know anything, just the definition. So with that you cannot hope to prove anything. Yeah. But if, as one says a C star algebra, you should have some picture in your mind, and therefore I am discussing these examples. I have described what the C star algebra is. The universality property I have not proved. After all, this does not define anything. One has to prove its existence and universality. So I have produced the C star algebra, universality will prove later, that's all. Fix a number q between 0 and 1. Then again, similar definition. This is the universal C star algebra. Generated by two generators, alpha and beta, such that they satisfy these conditions. So now, kind of from the previous example, you know what this means. This means this is a C star algebra generated by two elements alpha and beta. In that C star algebra, these relations are satisfied, and whenever we have a second C star algebra satisfying those conditions, there is a surjective map from this one to that one. So construction is also same. You can define that family and prove that so we take n naught to be this set and our Hilbert space to be small n2. Then this holds. Now define a homomorphism pi. And then you can verify that all those conditions are satisfied. And So this is finite. So you contract the first identity by xi from both sides. So this is norm pi alpha xi square, this is norm pi beta xi square. So from this you conclude both these quantities are this. So norm pi alpha, norm pi beta, both are less than or equal to 1. So if A is a word like some coefficient times a word in alpha and beta, whether this is a finite sum, then norm pi A is less than or equal to, because both alpha and beta have norm less than 1, so this is true. This proves that this quantity is finite, and so you can define a norm. This becomes a pre-sister algebra. So now I can define norm like supremum pi A. Pre-sister algebra means it is like a star algebra with a norm with the sister identity. So this is defined as the completion with respect to that norm. But of course, these two examples raises one question, which is, firstly, if I write down a kind of arbitrary words in a finite alphabet, so can we have sister algebras generated by arbitrary words? Okay. So suppose, for example, I give this word 2x star equal to x. This is a word. I have my alphabet x, and this is a word involving, or a sentence, x star and x. So of course this cannot be satisfied, because in this case, if I want to form this thing pi, so let us call this algebra say A, I can form a finite, and this set becomes empty, because norm of pi x star is same as norm pi x, so we cannot have this thing. Even if this is non-empty, if we take this word x star equal to x, then this set is non-empty, but that supremum is infinite. So the question is, given a collection of words, can you decide whether you can define a sister algebra satisfying those? That is the question. action of, say, relations. In a finite alphabet. But this principle works for even for infinite number of relations. So let us do that. Let gamma be a discrete group, and then C star gamma is the universal sister algebra generated by unitaries such that okay. So again one has to prove pi is non-empty, so you fix this Hilbert space small L2 of gamma and define UG of xi at S equal to xi of G inverse S. This shows this is non-empty, and on a finite sum like summation AG UG, pi norm is less than equal to summation mod AG. So the supremum is finite, so one can define a sister algebra.
Sorry, let me do my police thing 1 minute. Everybody knows what L2 of gamma means?
That is assumed.
No.
Meaning,
I'm questioning that. Does everybody know what L2 gamma is?
common action was.
Nobody saying anything. No, let me ask Krishna. And so,
No one did.
please say no. What is L2 gamma?
Okay, fine, no problem. I consider a vector space with basis gamma, and so its elements are like finite sums, summation AG, and let us call them, say, delta G, where G is in gamma, AG is complex numbers, and this is a finite sum. And then given two such things, I define their inner product to be, then this will give rise to a norm of,
Physicist or mathematician?
no, I am a physicist. In this case, I am always, operator algebra came from physics. Operator algebra came from physics. So its norm square is summation mod AG square. So you complete this vector space. That is called L2 gamma, and it has nothing to do with the group. I could have done this on any set. So this produces what is called the group sister algebra, and I have not said of anything about measures.
Counting now.
Great. So, now I want to discuss an interesting example. These are standard and available in books and so on and so forth. Now let us discuss something kind of which is interesting and yeah. So, idea of this subject, or I do not say this subject, some people, is the following, that one starts with a context, it could be anything, not necessarily operator algebras, and then one attaches operator algebras to that context, and then of course studies this and produces something, and this is, these remarks or the conclusion is relevant for the original context. And one such instance is the following. So, kind of, it is the goal of, one should not say goal, but to a large extent, arithmetic, it is like understanding of so we have this field Q, and so there is a group associated to it called the Galois group of Q, and understanding of this group is one of the major goals here, and to understand this group one wants to understand representations of this group, let us call it GQ. Now, what this context does is it produces sister algebras, and then out of that sister algebra there are some automorphism groups, and using those automorphism groups there are natural sets. Those gives rise to natural vector spaces, and on which this group acts. We won't go as far as the action of such groups, but we will just discuss the construction of the sister algebra, and I believe later on you will do KMS states or something like that, just the definition, they will just learn the statement. In your note there is something, I saw the KMS something.
Maybe I was hoping to, but not in the.
Not here? In the 6th lecture it says KMS. Anyway, so if you learn the definition of, then of course it's a pity we cannot even state that. So anyway, you will learn the sister algebra, and even that is remarkable. Even that is remarkable because you can produce some sister algebras using some number theoretic context. And again we will restrict, of course these things are possible to do in more generality than Q, but we will restrict ourselves for this case. What kind of, that is a major spirit of investigation today. So, let gamma be a discrete group, and gamma naught is an almost normal subgroup. So this means the following, almost normal means the following. So gamma naught acts on this space is the space of cosets like this. So gamma naught acts on this from left, and this action has finite orbits, and you verify it as an exercise. Gamma naught is normal if and only if every orbit has a single element. So in that sense it is almost normal. So that means if I look at a double coset, which is a set like this is a finite union of for some gamma 1, gamma 2, gamma k from gamma naught. Then the Hecke algebra is the convolution algebra of complex valued functions of finite support on. So these are space of double cosets. That is, we consider functions f from gamma to c such that f is bi-invariant and so therefore f will induce a function f tilde and f tilde has finite support. On this algebra, you define a multiplication law So in all the previous examples, the spirit is first defined in algebra, consider all its representations and then take their supremum. But this is kind of in the initial stage it goes like that and then it takes the other path. So firstly, why is this a finite sum? So what is that? Space of double cosets. So if you have a, space of double cosets, if you have a group G and then you have a subgroup H, then G decomposes as disjoint union like this and these are called space of double cosets. So a function on that is same as these bivariant functions, and so yeah, I will draw a picture so that it becomes easy. So we have this is the group gamma, and double cosets decomposes this group in an equivalence relation. So these are say gamma naught, G gamma naught, double cosets. Now every double coset again decomposes into a union of things like
Summation is over.
gamma 1. Gamma 1 is varying over this coset space. Yeah. So now this thing that these two are equivalent, okay, that the gamma naught action on has finite orbits is same as, of course, this is left action on these two facts are equivalent.
Sorry, what does F prime gamma 1 mean? Elements of functions on gamma.
These are bivariant, therefore you can choose any and it makes sense.
So you mean F prime tilde in the notation of the example?
Otherwise it will become terribly clumsy if you want to keep track of that. So you pick any representative, whatever common sense is, and it should work fine because these are bivariant functions. So gamma 1, the remark is that gamma 1 is something like gamma naught times G. So f prime of gamma 1 is defined as, otherwise gamma 1 is an equivalence class, but f prime of gamma 1 is defined as f prime of G. This is well defined because f prime satisfies this condition. So you can multiply from this side by an element of gamma naught. So every class decomposes into a, this is a finite decomposition, okay, into classes G gamma naught. Therefore, support of f prime contains finitely many of these double cosets. It is constant on each of these, and on each double coset there are finitely many such. Therefore, this is a finite sum because this quantity will give non-zero result for finitely many things. So each double coset is a finite union of left cosets and that's the condition of almost normality. Gamma naught is an almost normal subgroup of gamma. You should keep all the definitions in mind. And support of f prime contains finitely many double cosets. So these two together imply this is a finite sum, and this is yes. No, it will take some time.
Yeah.
It will take some time. It is.
When you say gamma naught is almost normal,
Yes.
does that mean that the double coset space is finite?
No.
So,
No, because I am not saying that this class is finite, right? I am not saying the space of double cosets is finite. I am not saying that. All I am saying is that within each single double coset, you are further partitioning in terms of left coset or right coset. That is finite.
So if you multiply
as support of f is finite, so from there you are already getting a finite number of double cosets, and within each finite double coset there are finite number of
So that
left
you are
coset.
trying to
Yes.
understand the reason for the requiring finiteness of support.
Otherwise this sum won't make sense, kind of, it will be infinite. Because just this does not imply that this is a finite sum. So you can restrict to support of f prime at the beginning, right? Because again, let us draw this picture. Double cosets will decompose the space, and then if I use left cosets, that gives a further refinement of this, right? So I am summing over left cosets. So all I need to prove is that there are finitely many left cosets on which this quantity survives. Now value on each left coset, say this one, f prime of that is same as f prime of this double coset, because f prime is constant on double cosets. So now let us count how many left cosets on which f prime can survive. So support of f prime anyway has finitely many double cosets. On each of them there are finitely many left cosets. So if we count all the left cosets on which f prime survives, that is finite. Is it clear? Yeah, because and this kind of notational passage from f to f tilde is always kind of happen. For example, this is a double coset, but I am evaluating on G and defining it like that. Yeah. So now we want to prove that this is bi-invariant.
When we discuss this, the problem, why is this in algebra? Why is this a
Yeah, exactly. So,
multiplication? Why is it well-defined multiplication? Why is it
no, it is well defined. No problem in the well definedness.
It is a finite sum.
Finite sum I just argued. I need to argue that it satisfies this bi-invariance condition. And then again, it is not difficult to see that it is finitely supported. So that condition I need to argue. So that's what I will do now. So this is bi-invariant. So let us try to compute this quantity. So bi-invariant means I need to prove this, that f star f prime gamma 1 g gamma 2 is same as g for all gamma 1 gamma 2 from gamma naught and g from gamma. So we write down this. So what is that? So we have already argued that this is a finite sum. Okay, so let us denote those things by gamma naught hj.
If you multiply two double cosets, then that will be union of double cosets. What will be multiplicity of different double cosets?
We do not know anything. It is just a symbol gamma naught. You cannot say. All you need to know is this is an algebra. Yeah. So this is so now I use maybe this notation, because all we know is that terms appearing here is a finite set. So I denote them by gamma naught h1, h2, hk. So use this. So this is same as f is bi-invariant, therefore I can forget this gamma 1, g gamma 2 hj inverse f prime of gamma naught hj, Now observe that gamma naught acts on this from this side. So these quantities, say, or gamma 2 inverse, so gamma naught acts from this on this side. So if I look at this thing, I define gamma naught H gamma 2 inverse H j equal to gamma naught H, let us call it gamma 2j, then this is actually a permutation of these indices. This is a permutation of these indices, and therefore this is f of g h gamma 2j inverse, and of course f prime is bi-invariant. Therefore f prime of gamma naught hj is same as f prime of gamma naught h gamma 2j. So this indexing set remains same. So this is same as f star f prime on g.
How did you put that? That's not a multiplication.
Which one is not a multiplication?
How did you bi-invariance go from?
Bi-invariance shows that these quantities, so if this happens, all I am saying is that f prime of gamma naught hj gamma 2 inverse is same as f prime of gamma naught hj, because this is from gamma naught.
What is the gamma naught of h gamma 2j?
So this is gamma naught of h gamma 2j, right? This coset is same as that coset. That is the definition of gamma 2j. Okay. So, which one? I did not conjugate by elements of gamma naught. No. Gamma 1, gamma 2, it is action of gamma naught cross gamma naught, yeah? After this line? So, f is bi-invariant, so I can forget this gamma 1. F is bi-invariant. So, you forget this gamma 1, it is this quantity. What? Yes.
For any gamma 1, gamma 2.
For any gamma 1, gamma 2, so I can take the entire thing as my g. Gamma 2, gamma naught has identity, so, okay? Yeah. So, no, it will take a while to familiarize with the manipulation, but it makes sense, and best way is really, you have more or less got the idea, nothing is very deep. All I am doing is just playing around with the definition. So you go home and then verify. It is not deep. That is the point. You need not copy or do anything. You go home and do it once by hand, then you see what it is. Yeah. So that is also finitely supported, so no problem. Proposition.
This example is not in your notes, is it?
No, this is not in the notes. When in notes, I just borrowed from his home page. Now, I will type these things and meaning by second week.
Even just have somebody scan it and give it to me and put it up on this home page.
Yeah, meaning I have handwritten notes, kind of very good handwritten notes. So
So you get somebody to scan it and give it to me.
yeah, because there are fundamental algebras coming also, because I am representing them in Hilbert spaces. So the following formula defines an I have not yet defined any involution in this, but I will do that. Involutive representation, say lambda of this in the Hilbert space small L2 of. So given any set, we can talk of small L2 of that set basically by that construction. So it is in this thing that lambda of f at xi acting on gamma is summation f, same formula, and this is a principle really, and where f star of gamma is f of gamma inverse bar. So involutive. Involutive means star stands for involutive, and convolutive I have not heard. It is convoluted. It is convoluted. Huh? H of gamma gamma 0 means that set with this multiplication law. So set of functions, finitely supported functions, and with that multiplication law. So the norm closure of lambda,
Clear that lambda f is bounded?
I will just remark that, of course. But of course, as you see, things are very much finitely supported. So the norm closure of this is denoted, say, C R star H of gamma naught, and this notation. So whenever we have some algebraic relations, we represent concretely in a single Hilbert space and consider its closure. That is always denoted by one R here. So maybe later on with groups I will make a remark. So as we have some relation, it is a star algebra. In all the previous examples we had a star algebra. We considered all possible representations and then defined the norm. Now we do not consider all possible representation. We consider one specific representation and then we close this. So this is always denoted by some reduced, R stands for reduced, and these are much easier to deal with, but of course the universal one has got its universal properties, so that also has got its advantages. So we need to prove that these are all bounded operators. Now, as in the previous case, meaning previous thing, so for how many terms this quantity can contribute? Gamma 1 is varying over cosets. So for how many terms this quantity can contribute? It is the same argument basically. It is a finite number of terms. Therefore, like you count all possible double cosets in the support of f, then inside each of them you put all these left cosets. So you count the total number. If that number is n, then of course you consider these sums like summation lambda f xi gamma mod square. Now of course gamma is varying over, that is crucial. Now you can kind of show that this sum is less than equal to, if that number is n, then it is like n squared times summation xi gamma square.
of f.
N of f, yes. So this will be bounded. So it does something, and now I will just state this result. Of course, I do not. I will not define. I will not define these things. If it is done later on, then probably it will make sense. At this moment, they may be somewhat backwards. So L gamma is the cardinality of. So all along we are decomposing double cosets in terms of left and right cosets. So cardinality of the image of gamma naught, gamma naught in gamma over gamma naught, and similarly R gamma. Then of course they take natural numbers as their values, and L gamma equal to R gamma inverse. And now this proposition which I won't prove, but it requires one definition. So we have a sister algebra, and on that sister algebra we say that there is an automorphism group. That means there is a homomorphism from real line to automorphisms of that. So maybe I write down the definition. An automorphism group of A is a homomorphism alpha from R to automorphisms of A such that for all A in A, this map T going to alpha T of A is continuous, and this is called maybe a one parameter automorphism group. Then proposition is the following: there exist unique one parameter group of automorphisms of CR star such that sigma t of f at gamma equal to, so kind of this comes with its spectral decomposition. So you understand the meaning of this proposition at least, and its relation with modular automorphism group is the following. This part you do not understand, and you just note down. If it is done later on, it will make sense. If it is not done, it will not make sense. Sigma of minus t is the so we have a sister algebra. This sister algebra sits inside B of this Hilbert space. So we can consider its double commutant that will give rise to a fundamental algebra. So is the restriction of the modular automorphism group for the state on so given any element in that set, we can form a vector in that Hilbert space, right? Given any element in that set, there is a vector in that Hilbert space. So using that vector we can form a state by contracting by that vector, and
He is that state.
phi is that state corresponding to gamma naught.
Vector state corresponding.
It is a vector state. So gamma naught is an element in this set. Therefore, on L2 gamma it determines a vector. So that vector state is phi, and for that the modular automorphism group at minus t is given by this. And now we discuss just one concrete instance of this, and that's what which kind of till now these are all abstract. Gamma is a discrete group, gamma naught is an almost normal subgroup, and so on and so forth. And when specialized, I just discuss one instance. So gamma is PQ plus and gamma naught is PZ plus. PQ plus is this one. Both are rational numbers. A is invertible and positive. And PZ plus is similar, but of course there are no positive integers other than 1, which is invertible. So this is like, okay. Claim is that gamma naught is almost normal in gamma.
You're forgetting the Q is abelian.
Oh, that's fine. Yeah. No, one can do this in matrices also. Yeah, so okay, I do this, but I wanted to discuss another example, but probably I will do that next time. Yeah, so suppose G is an element like this, 1, then this coset G gamma naught will look like, if you multiply, this is 1 n plus a k 0, where and if I take another element from gamma naught, so say 1 n1 1 0 g gamma naught, then that will look like 1 Now these quantities n1 k, as n1 is varying over z, k is a rational number, but as n1 is varying over z, modulo z it can take finitely many values. So So that shows that these cosets are actually finitely many. Or do I continue, or because inductive limit I wanted to talk about.
You can do it in 7 minutes.
Meaning you can do it in 7 minutes, why not?
But in a way that across.
No, I think then we should do it next time because it is an important construction. So
Okay. You mentioned KMS, so I will not say anything about KMS, but I will talk about the modular group.
that is fine.
Just tell them.
Now, why this non-commutative
If KMS is necessary, meaning Then one can go for the even this next step. How does Galois group come? Because now there is no Galois group around.
Why this not commutative torus having something to do with torus? I mean, is there, it's just change of equation, that's why,
If you put theta equal to 1, or theta equal to 0, right? Or 1 or any integer, then it will give you that. Function algebra of torus, yeah.
What is the reference for this?
This is Bost, for this is reference is Bost-Kohn Selecta Mathematica. I think sometime in 95. Yeah, meaning in that paper this game started, and
is that polynomial factor in some cases?
it is a factor. It is of type 3. Yeah. Yeah, maybe type 3, 1.